So what is a knuckle or front upright? The knuckle holds the wheel onto the front corner of the vehicle. Because of this, the weight of each corner must pass through it. The front wheels are rotated by implementing a force through the steering arm in each knuckle, so it must resist steering forces. The calipers to each wheel are attached to the knuckle and thus must support moment generated by braking. The knuckle also must be rugged. We never know we're going to see a competition, so a relatively high safety factor is needed. In order to explain our loading constraint scenarios, the anatomy of the front corner must be explained. The knuckle is mounted to two rod ends. One connects to the upper arm while the other connects to the lower arm. An axle is pressed into the center of the knuckle and is what the hub rotates about. Crude representations of a brake caliper and rotor were added for ease of loading. Finally, a rack and pinion is attached via a tie rod to the steering arm, and therefore is what receives the steering input. Our knuckle will be machined from 7075 aluminum, which has a tensile strength of 83,000 psi and a yield of 73,000 psi. We wanted to test out 3 different loading scenarios that the knuckle is likely to see. These scenarios are a 5G vertical load to the spindle bore, which simulates a hard landing impact, and a scenario for both turning and braking. To simulate each scenario, different loading and constraint conditions were used. In the 5G landing, the upper and lower rod end bolts are cylindrically constrained radially, with the tangential movement free. The lower bolt is constrained axially, while the upper is free. A force of 2,000 pounds is used in the positive y direction. 2,000 pounds is 5 times the weight of the vehicle. For the turning scenario, the same constraints are used, except the axle bore is constrained with a cylindrical support. It cannot move radially, but is free to move tangentially and axially. A 100-pound force in the negative x direction is shared by both tabs. Finally, braking is simulated using the same supports as a 5G landing case, but has a 1,935 inch-pound moment about the representative rotor.
Shown here is the FEA results for the 5G vertical load to the spindle bore. This simulates impacts due to rough terrain, whoops, jumps, and drops. The maximum stress was around 20,100 psi at the lower A-arm connection point, which is the expected location for the maximum stress due to the lower A-arm being the main load-bearing member in the front suspension. This gives a factor of safety of approximately 3.5. Since the loads used in this analysis were intentionally overestimated, this means that the design will not fail due to such loads. On the right-hand side of this, you can see the total displacement convergence. We started at a 0.5-inch mesh and moved to a 0.1-inch mesh, and you can see that the total displacement increased. Here's the equivalent stress results due to the steering forces on the steering arm. As you can see, the maximum occurs at the base of the steering arm and is approximately 6,960 psi. This gives a factor of safety of about 10.5. This is a very large factor of safety, however, it does not take into account the cyclic nature of the stress. Also, for Baja, large safety factors are often necessary because oftentimes scenarios occur that could not be predicted, and the weight savings gained from optimizing the steering arms is not worth the risk of failure. This shows the equivalent stress results for the moment due to braking. The maximum occurs at the lower A-arm connection. However, it is important to note that there are also high stresses in the caliper mount. Initially, the max stress was actually at the caliper mount where the probes are shown. However, as the mesh was refined, the stress concentrations at the mount were corrected as well, and the max stress shifted to the location shown currently. This maximum has a value of about 12,349 psi, creating a safety factor of about 5.9, again indicating that this section of the part will not yield under these loading conditions. In conclusion, the maximum stress was found to occur during a 5G loading and can be safely assumed to not cause the part to yield. The shifting of the maximum location as the mesh was refined highlights the importance of refining a mesh to ensure the stress concentrations are accurately represented. In order to completely validate this design, further analysis such as fatigue analysis would need to be done. However, due to the large safety factor found using an overestimated loading scenario, and due to experience with previous designs, we believe it is safe to say that this part will not yield. One last important thing to note is that the true maximum stresses could be greater than or less than those shown. As shown, the displacement converges to a larger value as the mesh is refined. However, stress can either increase or decrease further with refinement.